Hello everyone, this is the part 2 video for amplitude modulation. Let us visualize it. In the part 1 video, we have seen the basics of communication model, definition for modulation and the need for it, and we have also seen the introduction to amplitude modulation. In this video, we are going to see the mathematical representation for amplitude modulation, conditions to be satisfied for amplitude modulation, and its MATLAB code. Now, let us recall what is amplitude modulation. Amplitude modulation is the process of changing the amplitude of the high frequency carrier signal accordance to the amplitude of the low frequency message signal, so that the modulated signal have the frequency of the carrier signal and its amplitude varies in accordance with the amplitude of the message signal. First, let us write the mathematical representation of amplitude modulation. Here we have assumed that the input signal is a low frequency sinusoidal signal. So the mathematical equation for the low frequency sinusoidal signal can be written as Vm of t is equal to Vm into sine 2 pi Fm t, where Vm is the amplitude of message signal and Fm is the frequency of message signal. Here the m represents the message signal. Similarly, the carrier signal can be written as Vc of t is equal to Vc into sine 2 pi Fct, where Vc and Fc are the amplitude and frequency of the carrier signals respectively. Here, the C represents the carrier signal. So, we can write the message signal as Vm of t is equal to Vm into sine 2 pi Fmt, and the carrier signal as Vc of t is equal to Vc into sine 2 pi Fct. Similarly, the modulated signal can be written as Vam of t is equal to Vam into sine 2 pi Famt. We know already the frequency of the modulated signal and the frequency of the carrier signal is similar. So the above equation can be rewritten as Vam of t is equal to Vam into sine 2 pi Fct. So our objective is to find the amplitude of the modulated signal Vam. I repeat, the message signal Vm of t is equal to Vm into sine 2 pi Fmt. The carrier signal is Vc of t is equal to Vc into sine 2 pi Fct, and the modulated signal is Vam of t is equal to Vam into sine 2 pi Fct. When we observe the modulated signal, we can say that the amplitude of the modulated signal is varying in accordance with the amplitude of the message signal. So, the amplitude of the modulated signal can be written as the sum of the amplitude of the carrier signal plus the message signal. So, Vam is equal to Vc plus Vm of t. We know that Vam of t is equal to Vam into sine 2 pi Fct. Now substituting the equation for Vam of t can be written as Vc plus Vm of t into sine 2 pi Fct. Now let us substitute the equation for Vm of t, and the above equation can be rewritten as Vam of t is equal to Vc plus Vm into sine 2 pi Fmt into sine 2 pi Fct. Taking Vc commonly outside from the first term, the above equation can be rewritten as Vam of t is equal to Vc into 1 plus Vm by Vc into sine 2 pi Fmt into sine 2 pi Fct. Now considering the ratio Vm by Vc as m, the same equation can be rewritten as Vam of t is equal to Vc into 1 plus m sine 2 pi Fmt into sine 2 pi Fct. Here, m is the modulation index, which is the ratio of amplitude of the message signal and the amplitude of the carrier signal. These two equations are used as the mathematical equations for the amplitude modulated signal. So the mathematical equation for the amplitude modulated signal can be written as Vam of t is equal to Bc into 1 plus m into sine 2 pi fmt into sine 2 pi fct. So these three equations are the mathematical representation of the corresponding signals, and we are going to use these three equations to write the MATLAB code. Now let us move ahead and start writing MATLAB code. Before going into it, let us see the step-by-step procedure of it. Step 1. Create the low frequency message signal. Step 2. Create the high frequency carrier signal. Step 3. Create the modulated signal. And step 4. Demodulate by using envelope detector. There are many demodulation techniques, and here we are going to use the envelope detector as the amplitude demodulator. Our objective is to plot the low frequency message signal, high frequency carrier signal, the modulated signal and the demodulated signal. Here we are going to use envelope detector as the demodulator. Finally, we are going to verify whether the message signal and the demodulated signal is similar or not. Now let us start writing MATLAB code. Open MATLAB first. Select new script. This is the editor window and this is the command window. I'm going to type the program here, and this is the workspace. Now let's move ahead and start writing the program. CLC, which is used to clear the command window. The previous values available in the command window will be deleted. First, let me save it. As amplitude modulation, and for running the program you can either click on this green button or else you can press F5. So the previous values available in the command window got deleted, and the next command is clear all. This clears the previous available values available in the workspace. Let me run again. Now we can see the previous data available in the workspace got deleted. Now let us define the time period for the continuous signals. T is equal to LIN space of 0, 0.02, 50,000. That is, between the point 0 to 0.02, 50,000 points are selected. Okay, let us run now and see how the T appears. So totally we have 50,000 values between the point 0 to 0.02. We know the first step is creating the low frequency message signal. So step 1, message signal. Let the amplitude of the message signal be 7 and the frequency of the message signal be 200. We know the equation for message signal. Vm of t is equal to Vm sine 2 star pi star Fm star t. Now let us plot the message signal by using the function plot of t, message underscore signal. So this is my message signal, and this is the time period and this is the amplitude. So let me label it. X label time, Y label amplitude, title message signal. As I said already, in the single figure window, let me plot all the signal like this. That is, in the single figure window, I am going to plot the message signal, carrier signal, modulated signal and the demodulated signal. For that, I am going to use the subplot function, subplot of 4, 1, 1. That is, the figure window is divided into 4 rows and 1 column, and at the first place the message signal is plotted. The step 2 is creating the high frequency carrier signal Vc sin 2 pi fct. So step 2, carrier signal. Let the amplitude of the carrier signal be 8. Frequency of the carrier signal be 4000. We know the equation for carrier signal. Vc of t is equal to Vc sine of 2 pi Fc t. I am going to plot it in the second place. So subplot of 4, 1, 2, plot of t, carrier signal, X label time, Y label amplitude, title carrier signal. Let me run it. So this is the low frequency message signal and this is the high frequency carrier signal. Let me represent the carrier signal with some different color, magenta. So the one which is blue in color is the message signal and the one which is magenta in color is the carrier signal. Step 3 is creating the modulated signal by using the equation Vc into 1 plus m sin 2 pi fmt into sin 2 pi fct. Step 3, modulated signal. We know the equation for the modulated signal. Vc into 1 plus m sin 2 pi fmt into sin 2 pi fc t. And I am going to plot it in the third place. Subplot of 4, 1, 3, plot of t, modulated signal, and let me represent by using some different color G, green, X label, time period, Y label, amplitude, and title as modulated signal. Okay, let me run it, and here we are going to expect an error. The error is undefined function or variable m. We know m is the modulation index, which is the ratio of amplitude of the modulated signal and the amplitude of the carrier signal. So I'm going to define M here, Vm by Vc. And let me run again. As we have seen earlier, the modulated signal amplitude varies according to the message signal. And final step is demodulation by using envelope detector. Step 4, demodulated signal. We are going to demodulate by using peak envelope detector. Demodulated signal is equal to envelope of modulated signal, comma 500, comma peak. Here the 500 represents peak separation sample parameter. I am going to plot this in the fourth place. Subplot of 4, 1, 4. Plot of t, demodulated signal. And let this be in red color. X label time, Y label amplitude, and title demodulated signal. Let me run again. We got the demodulated signal and we can observe that the message signal and the demodulated signal is similar. Now let us see how this demodulated signal is developed by using the envelope process. So I am going to add some more lines here. Hold on. And let me copy and paste this line here. Plot of t, demodulated signal, red with double dash line, hold off. Yes. So when we run this, you can able to understand how this envelope is created. So this is how the envelope is created. From the modulated signal, the upper envelope is traced out, and finally that is plotted as the demodulated signal here. We have seen the MATLAB code for amplitude modulation. Now let us see the effect of modulation index on amplitude modulation. We know modulation index is equal to Vm by Vc. When modulation index is less than 1, that is, when Vm by Vc is less than 1, we can say Vm is less than Vc, and this is called as under modulation. In this case, we can able to recover our message signal. When modulation index is equal to 1, that is, Vm by Vc is equal to 1, that is, the message signal amplitude and the carrier signal amplitude is similar, we say it is critical modulation. In this case also, we can able to recover our message signal. When modulation index is greater than 1, that is Vm by Vc is greater than 1, that is Vm is greater than Vc, then we say it is over modulation. In this case, by using the envelope detector or by using the demodulation techniques, we can't able to recover our message signal. Now let us move back to MATLAB code and let us change the amplitude for message signal and carrier signal and see how modulation occurs under modulation, critical modulation, and over modulation. Now let us change the amplitude of the message signal and the amplitude of the carrier signal, and let us observe the modulated signal and the demodulated signal. Before that, let me display the modulation index in the command window. Disp of M. So this displays the modulation index M in the command window. Till now we have considered Vm is equal to 7 volts and Vc is equal to 8 volts. That is Vm is less than Vc. This is called as under modulation and the modulation index is less than 1 and we can observe that the message signal and the demodulated signals are similar. Now we'll consider the critical modulation. In critical modulation Vm is equal to Vc. Let me run again. In this case, the modulation index is equal to 1 and still we can observe that the message signal and the demodulated signals are similar. Now let us assume that the Vm is greater than Vc, which is called as over modulation. Let me change the amplitude of the carrier signal as 5 volt. Let me run again. In this case, the modulation index is greater than 1 and when we observe the message signal and the demodulated signal, both are not similar. So the condition for modulation index in amplitude modulation is modulation index should be less than or equal to 1. So the modulation index should be less than or is equal to 1 so that the message signal and the demodulated signal will be similar. Now let us explore more about amplitude modulation by using graphical user interface. Till now, we have considered the frequency of the carrier signal is greater than the frequency of the message signal. And this graphical user interface will help you to understand what happens when the carrier frequency is lesser than the message signal frequency, what happens if there is no message signal, and what happens if there is no carrier signal in amplitude modulation. This is the graphical user interface which can let us to understand more about amplitude modulation. This message panel can be used to control the amplitude and the frequency of the message signal. Similarly, this carrier panel can be used to control the amplitude and the frequency of the carrier signal. First, let me plot the message signal. The message signal is having the amplitude of 7 volts and the frequency of 200 Hz. Next, let me plot the carrier signal. The carrier signal is having the amplitude of 8 volts and the frequency of 3200 Hz. And this is the modulated signal. This is the envelope of the modulated signal which acts as the demodulated signal. Next, calculation of modulation index. We know already modulation index is defined as the ratio of amplitude of message signal and the amplitude of the carrier signal. In this case, the modulation index is less than 1, that is 0.875, which is under modulation. As we have seen earlier, whenever the modulation index is less than or equal to 1, then the message signal and the demodulated signal is similar. Now, keeping the amplitude of the message signal constant, I am going to reduce the amplitude of the carrier signal, and we can observe that whenever the modulation index becomes greater than 1, the message signal and the demodulated signal differs. That is, the transmitted message signal cannot be received at the receiver side correctly. Till now, we have considered the frequency of the carrier signal as the higher frequency. Now let us see what happens when the carrier signal frequency reduces. So, when we reduce the frequency of the carrier signal, we can clearly observe that the modulated signal is not as like we have expected, and hence the demodulated signal is not similar to that of the message signal. So the conclusion is the carrier signal frequency should be higher for amplitude modulation. Now let us observe what happens when there is no message signal. When message signal amplitude is 0 volt and frequency is 0 Hz, we can observe that the carrier signal and the modulated signal is similar. And this is the envelope of the modulated signal, and hence the demodulated signal have 0 amplitude and 0 frequency. Now let us see what happens when there is no carrier signal. When we don't have the carrier signal, the graphs clearly show that the modulation cannot be done, and the demodulated signal doesn't have any information about the message signal. This is the graphical user interface created by me for quick understanding of amplitude modulation. We can also change the amplitude and frequency of message signal and carrier signal in the MATLAB code to obtain the same result. So, in amplitude modulation, two conditions should be satisfied. The first one is the modulation index should be less than or is equal to 1, and the second one is the frequency of the carrier signal should be greater than the frequency of the message signal. Till now, we have considered the channel as the noiseless channel. That is, the modulated signal is demodulated as it is. But in the real world, the channel didn't transfer the information as it is. Instead, it adds some noise along with the modulated signal. Try writing a code by considering noisy channel for the message signal with amplitude modulation and without amplitude modulation. When you do so, you can clearly observe that there is a drastic difference between the signals with amplitude modulation and without amplitude modulation at the receiver side. Solution for this, along with some graphical user interface, applications for amplitude modulation, advantages and disadvantages of amplitude modulation will be continued in part 3. Hope you enjoyed this video. Thank you for watching.